Good morning. Wow, kind of loud. It's a pleasure to be here. How many of you, let's start with a quick poll. How many of you have in the past built an application for the cloud where you used a cloud resident database as your application for your application? Okay, now those of you who have your hands up, in how many of those cases was it ever a NoSQL database? And how many of you wish that you could use transactions in your applications to make your life easier? Exactly. So what I'm going to do today is talk about why it is that cloud databases, particularly NoSQL databases that were designed for massive scalability, why is it that they don't support transactions? Is it that transactions are fundamentally at odds with scalability? Why can't we have both? And for me, this is not simply an academic question. I started pondering this question about 2 years ago when I took responsibility for designing a transaction system for Amazon DynamoDB. DynamoDB is the AWS infinitely scalable database service that runs in the cloud. It powers a lot of our internal applications and a lot of external customers for AWS. And I had to ask the fundamental question as I was designing it is, can I add transactions to DynamoDB without breaking the fundamental tenets of DynamoDB, which are high scalability, high availability, and low latency performance? But before I tell you how I did it, let's start with some background. Databases are moving to the cloud at an astonishing rate. Enterprise customers are quickly moving off their on-premises databases to the cloud. Startup companies invariably start from day one in the cloud because the benefits of being in the cloud are just too compelling. If you want to have a database, you want to use a cloud database service, it's fully managed in the cloud, which means that you as the data scientist, you as the application developer don't have to worry about bringing up and managing your own infrastructure. The cloud provides automatic provisioning of resources and elasticity. So as your workload of your application changes, your service will automatically grow and shrink to meet your application needs. Offers a pay-as-you-go model which appeals to both large and small companies. The bottom line is that the cloud provides the agility that modern companies need and want for managing their data that drives their businesses. But as these companies are moving to the cloud, a lot of them have chosen to forgo relational databases and have instead adopted something called NoSQL databases. So what do I mean by NoSQL databases? NoSQL databases have several characteristics that are in tune with the cloud. Perhaps most glaring is they don't provide a relational model or relational interface. Instead, they provide a simple model. Typically, it's known as a key value store. Each item in your database has a key, has a value which may be totally unstructured data in the case of a blob store, or it may be structured data like a JSON object. The operations for operating on these store are typically simple. Get operation for reading the value of an item given its key. A put operation for writing the value of an item given its key. These are in contrast to what you see in a relational database where you have SQL statements. And that's why these things are called NoSQL databases, though lately that term has become a little bit of a misnomer because a lot of these NoSQL databases now in fact support queries of various forms, but we still call them NoSQL databases. Another thing that they provide, which is different than relational databases, are a completely flexible schema. So if you want, you can take your NoSQL database, you can take the same table in it, and in that same table you can store customer records, bank transactions, photos, your social network graph. You know, I'm not recommending that, but I do see customers that do that, and there are in fact some benefits for storing a lot of different types of data in the same tables. One of the key stalwart properties of a NoSQL database is high availability. If you run in the cloud with one of these databases, invariably your data is replicated at least 3 times. 6-way replication is not uncommon. So for instance, in DynamoDB, my favorite NoSQL database, we will take your data, we'll take your table, replicate it across 3 what we call availability zones. Each availability zone runs in a separate data center with separate networking, separate power. We can lose a complete data center, and still you can read and write your data in DynamoDB because it's replicated in 2 other data centers. And if you really want more replication than that, we provide something called global tables, where you can take your DynamoDB table, replicate it not only within 3 availability zones, but asynchronously replicated across regions throughout the world. If you use normal DynamoDB replication, we offer 4 nines of availability. If you use a global table, we offer 5 nines of availability, which is higher than anything I've seen any relational databases offer. Another key property of NoSQL databases is unbounded growth. Okay? DynamoDB, you start with a table, you create it, you don't tell us how big that table is going to be, you just tell us what the table name is, what the primary key for that table is. Your table starts out as all your data in one partition on one machine, well, 3 machines because it's replicated. As you start putting information into that table, it grows. As it grows, we will automatically take that data and partition it across as many machines as we need to keep the data widely of reasonable size. So your 1 partition eventually becomes 2, 2 becomes 4, 4 becomes 8, and so on. But you as the customer never see this happening. It just happens automatically under the covers. And then the final thing is, because we keep partitions small, and because of this simple API that does gets and puts on individual items, we can provide predictable performance. And that's pretty standard across NoSQL data stores. In the case of DynamoDB, we advertise performance of less than 10 milliseconds for get and put operations. And that's independent of the size of your database. Whether you have a database that's a megabyte or 100 terabytes, we still provide the same performance for your gets and puts. These last 2 properties are what I'm calling scalability in this talk. The ability to store arbitrary amounts of data in a table. We have tables that go up to petabytes, and the ability to have performance that you could depend upon independent of the size of your table. And the question is, can we provide scalability, or can we provide transactions in a NoSQL database while maintaining the scalability properties? That was the question I wrestled with. Why do we want transactions? Those of you who have used transactions know that they're wonderful. They help developers write correct, reliable programs that want to maintain invariants that span multiple items in your database. These types of multi-item invariants are all over in applications that you look at. So for instance, if you do a social networking application like Facebook, you may have the invariant that if Mary is Bob's friend, then Bob is also Mary's friend. If you have a banking application, you may have the invariant that you want to maintain that if Bob gives Mary $50, then at the end of that transfer, the amount of money total in Bob and Mary's account is the same as it was before the transfer. Maintaining these invariants in a distributed system is really hard, okay? It's hard because you have multiple instances of your application invariably in the cloud that are running in parallel, all sharing the same data, all trying to access it concurrently. You'll see applications on AWS that have thousands of instances because they need that many to handle the load of a large user community, or because they want fault tolerance for their applications. And maintaining invariants is hard because of failures. Failures are a fact of life in the cloud. Machines are always failing. It'd be nice if the application developers didn't have to explicitly deal with failures or deal with concurrency, and that's what transactions buy them. Transactions offer the ability to deal with concurrent access and to deal with partial failures without the application developers having to write a lot of non-application specific code. And they do this by providing 4 properties that you've probably heard of before called the ACID properties. The ACID properties are atomicity, which says that if you have a set of operations that are part of your transaction, either they all get executed or none of them get executed. Correctness or consistency, which says that the set of operations move your database from a correct state, one where the invariants are maintained, to another correct state where the invariants are maintained, and no one ever sees the intermediate states where they may see invariants that are violated temporarily. Isolation says that if you have 2 concurrent transactions executing, They appear to execute in some order. That's known also as serializability. And finally, durability says that if your transactions update data, which they invariably do, then those updates are persistent and permanent. So the textbook example of using transactions that you learn about in schools is a banking application. So I'm going to use that today. Suppose we have a bank and it wants to store its data in a NoSQL database. There's an entry in this database for every customer of the bank. The primary key is the person's name. The value is the balance of their bank account balance. So here we have an example where Mary has $25 in her bank account. Bob has $100 in his bank account. And now if Bob wants to transfer $50 to Mary, then Mary's bank account gets updated to be $75. Bob's bank account gets decremented to be $50, and we'd like to do that as part of a transaction. It's easy to do that in a NoSQL database, like DynamoDB, with 4 easy statements. You can do this probably the same 4 statements in almost any NoSQL database. You need 2 statements to do a get, to read the current values of the 2 parties involved in the transfer. And then you add $50 to Mary, you subtract $50 from Bob's amount, and you write those back into your database using put statements. You could do that on DynamoDB at any time in the past throughout DynamoDB's history. But if you had written these 4 statements in your application, they may not have provided the outcome that you would have expected. For one thing, there's no guarantee without atomicity that your whole of your statements are going to execute. Your application may crash after updating Mary's account, but before updating Bob's account. In this case, Bob would be really happy because he gets to keep his $50, but the bank probably is not going to be really happy with that. Another example, without isolation, it's possible that you start running these statements in your application, you get the first 2 gets done, and then your application gets halted for some reason temporarily. Meanwhile, while it's not running, another application comes along and tries to deposit $100 in Bob's account. And now when you go back to the transfer after this deposit is done, and you do the last 2 statements that put the new values into the account, this put doesn't know that that deposit was done. And so in this case, Bob would be really unhappy because his deposit basically got undone by the last 2 puts. Okay, so this is an example of a problem that you get without isolation. Simple solution to that is to take these 4 statements and wrap them in a transaction. Say begin transaction, you do your 4 statements, you say commit transaction, and all the problems are solved for you. As simple as that. It's easy for the developers. And the question then is, why have NoSQL databases not just done this routinely? What's the issue? There are several concerns I've heard people express. One is, as I said, a key property of NoSQL stores is predictable performance. And customers really, really care about predictable performance. They want to know exactly how slow their application is going to run, or how fast their application is going to run if you're on AWS. As I said, we've got that already for get and put operations. When you start adding transaction operations, there's a question, because transactions clearly are fundamentally more complex than simple get and put operations. Can we execute transactions with predictable performance? Transactions have, potentially a large set of items that they have to access on a large number of storage nodes. There's concerns that the cost of a transaction, the performance of a transaction may depend on the size of your database, as I've seen in some systems. And so people were just really leery about adding transactions to a NoSQL database. The other fear that they have is that transactions will add complexity. There are hundreds, millions of NoSQL database applications out there that don't use transactions today. They haven't had the ability to use transactions. They don't care about using transactions. If somehow adding transactions to the underlying database that they're using breaks their application in some way because it fundamentally damages some property that they care about, that would be a bad thing. And so it's very concerning to add a complex feature like transactions to an existing system that's known for its simplicity. And so people also express concerns about the complexity of the underlying system, concerns about introducing concepts like deadlock or starvation or interference by running transactions. All of these may adversely affect availability, may cause us to violate some of the SLAs that we provide. We don't want to do that. And then finally, there's a concern about cost. Just not only the cost of the system as it becomes more complicated, the cost of operating that system, the cost of maintaining that system, and the cost of having to bill customers for the transactions, and what does that billing model look like? Okay, and so given these concerns, if you look at existing NoSQL databases, they have either shied completely away from providing transactions, or they provide transactions in a limited way. For instance, some systems have used isolation models that are less powerful than full serializability. Some systems have introduced transactions but restricted them to some subset of items. So for instance, there's a well-known system that allows transactions only on data that hasn't been partitioned. There are other systems that allow transactions only on items that happen to fall within the same partition. So for instance, there are systems that use stored procedures to implement transactions, and if you use a stored procedure, then clearly it only runs on a single machine, and that's the scope of your transaction. Once you get off that machine, you can no longer run transactions across those items. And there are systems that use transactions, but only on well-defined groups of storage nodes. So when I looked at this, I decided that this wasn't going to work for DynamoDB. We needed a better approach. We have customers who want full ACID properties for transactions. We have customers who are trying to, it's I think, well known that Amazon is trying to move its internal applications off relational databases onto DynamoDB so that we can get, our history suggests that by doing that, we get better performance for those applications, better availability, better scalability, and reduced costs. And our customers have noticed this as well. And so many of our customers are moving off relational databases onto DynamoDB. But one of the key impediments they face, of course, is that they're used to a relational system that has transactions. DynamoDB historically hasn't had transactions. So by adding transactions to DynamoDB, we can reduce the cost of migrating these applications. But only if we provide full ACID properties and full generality for transactions. And so when I sat down to design transactions, I came up with the following goals. We wanted to be able to support arbitrary sequences or sets of DynamoDB operations that can be performed atomically and in a serializable execution on arbitrary items in arbitrary tables within a region with predictable performance and without any impact on those applications that already exist that don't want to use transactions. People looked at me and thought, you're crazy. Okay, no one actually thought that we could do this. I'm going to tell you how we did it, but give me a second. If you look at the standard approach about how people go and add transactions to a system, here's what you would do. You would add two new calls, one that begins a transaction, one that commits a transaction. You could take your existing statements, wrap them in these two new calls to define a transaction. For statements that don't end up in a transaction, you can treat them as singleton transactions. Okay, so you automatically run them through your transaction protocol. They auto-commit. You're done with that. In terms of isolation, you use two-phase locking. In terms of atomicity, you use two-phase commit protocol. And then more and more, a lot of these systems are using multi-versioning at the storage layer so that you store a whole history of the values for a particular item. What that allows you to do is allows you to run read-only transactions on that item without those read-only transactions can read from a snapshot without interference from ongoing writes that are happening. So this would be the standard approach that we could have taken. I rejected all of these for Dynamo. We didn't do any of these. having general transactions where you begin a transaction and then can keep that transaction open for an arbitrary length of time. It's known as a long-running transaction. That ties up resources. DynamoDB is a multi-tenant system. I don't want any operations that can tie up resources for indefinite amounts of time because those resources may be needed by other customers who are using the system. I didn't want to take individual operations and just routinely run them through the transaction protocol because that's going to add performance overheads and have an impact on customers who don't care about transactions. So that's not a good idea. Two-phase locking introduces concerns about deadlock and starvation, which in turn introduces concerns about availability and violation of SLAs. So we didn't want to do that. Clearly, we need some sort of two-phase protocol, but I wanted something different than the protocol where you do a bunch of writes, and then at the end, you run a separate two-phase protocol to commit them. And multi-version concurrency control, I'm a huge fan of multi-version concurrency control, but it was out of the question because DynamoDB doesn't support multi-versions. Adding a multi-version store to DynamoDB was just outside of the realm of possibility for this project. It would be too costly and introduce other effects that we didn't want to introduce. And so we didn't do this. And so what did we do for DynamoDB? What we did is we added 2 calls to the API, one that supports read-only transaction, one that supports write transactions. These calls allow you to take a bunch of DynamoDB operations, package them up, send them out to the service in one shot. So they're called one-shot transactions. They either execute immediately or they get rejected immediately because they get rejected in the case where there's some ongoing transaction that's conflicting with this one, and therefore we can't execute this one immediately. These one-shot transactions look a lot, in theory, like the mini transactions that you may have seen in Synthonia. And Synthonia has shown us that one-shot transactions are useful for a variety of applications. So we mimicked that for DynamoDB, but we provided additional implementation or a totally different type of implementation, as you will see in a minute. So the 2 types of calls I said are transact get items, which allows you to take a bunch of get operations, package them together. Those get operations could be on arbitrary items in arbitrary tables, and we read from a consistent snapshot. These reads are serialized with respect to other transactions in the system. And the other operation is transact write items, which allows you to take DynamoDB put statements, update statements, and delete statements. So put totally overwrites an item, delete totally gets rid of the item, update allows you to do things like increment particular attribute values or change attribute values or to do incremental updates to the contents of an item. And then in addition to those 3 types of statements that you can have as many of them as you want in the transaction, well, currently we have a limit, but in theory we could. We also allow you to introduce a condition check into the transaction that the condition has to be met before the transaction is allowed to apply, okay? So we first check all the conditions. As long as the conditions are met, we then perform all the operations atomically in this transaction. DynamoDB already supported conditional updates, conditional put statements. You can do things like if this item exists or this item doesn't exist, then do this put. If it has certain value for this attribute, if this attribute is a numerical value and it's in this range and so on. We took all of those types of conditions and we allow you to put them explicitly as a precondition on the transaction. So you may be wondering, what's the limitation of these single-shot transactions? What can't I do in a single-shot transaction? And are they really limiting from an application developer's point of view? So as an example, on the left here, I show our transaction we wanted to write for our bank transfer, right? How would I write this as a single-shot transaction? It's actually pretty straightforward. I show it on the right here. What you do is outside of the transaction, you do the gets that you want to get the 2 bank account balances. Inside the transaction, you do the puts, and you also put 2 checks inside the transaction to make sure that those values you read outside the transaction haven't changed at the time that you want to do the transaction. It's as simple as that. I have yet to see a transaction that any of our customers have proposed where I can't rewrite them in this way. And in fact, this mimics how a lot of transaction systems are implemented anyway. I've seen a number of transaction systems that are implemented where you go, you do a bunch of reads, you record all your read sets, you buffer up all your writes, and then at transaction commit time, you validate your read set, you perform the buffered writes. This is exactly what's happening in this transact write items request right here. So let me give you another example. Here's an example that you think may be more akin to the kind of transactions that we run within Amazon. It's a shopping example. In this example, we have 3 tables. Customers table that stores all information about customers. We have an orders table that has a record in it for every item that's been purchased. And we have an inventory table that says for each item that's available for purchase, how much of that item is in inventory in the warehouse. Now, if Susie wants to come and buy 5 copies of a book for her book club, here's the transaction that may get done on her behalf. This transaction first checks that Susie is in the customers table, uses an exists clause. It then checks that there are at least 5 copies of this book that she wants to buy in the inventory. And then it puts an item in the orders table to indicate that she's buying these 5 copies of that book. And it updates the inventory table to subtract 5 from the amount of the book in inventory. Okay? So some things you will notice about this particular example is we're doing a check on the customers table, but we're not ever updating that customers table. We just do a check as a precondition for the transaction. We do a blind put on the orders table. We never do a check on the orders. We just are appending things to the orders table, so we don't care about doing blind writes to it. So this shows that the power of this single-shot transaction mechanism, if you allow it to contain arbitrary operations on arbitrary tables, is much more powerful than what you get, for instance, with an atomic compare and swap operation, even a multi-item compare and swap. Okay, so that gives you the flavor of the API that we provide to customers. You can go use it today in DynamoDB. What I'm going to do now is show you a little bit about how this is designed and operates under the covers. In order to do that, let me first talk about how DynamoDB works without transactions, and then I will talk about how we added transactions to it. So in DynamoDB, we have applications running. These applications submit operations like put, get, delete. These operations go through a front-end load balancer. They get sent eventually to one request router of a whole fleet of request routers. We have thousands, literally, of request routers running in the cloud. Each request router can process a single operation, each operation gets handled by a single request router. The request routers clearly are handling lots of operations in parallel. In the case of a put here, the request router looks up some metadata based on the table and the key of the item being put, where that item is replicated on which storage nodes. There are 3 storage nodes we call for each item. One of those is designated as the master storage node. The request router then looks up the master, sends the put operation to the master storage node. The master storage node then is responsible for making sure that that put gets applied and replicated across the other 2 storage nodes. When a quorum of the storage nodes have applied the put operation, it returns back to the customer saying it's completed. Now, when we added transactions, we introduced another step in this process. We introduced a fleet of transaction coordinators. So if a transaction requests one of these read-only transactions or write transactions, hits a request router in the usual mechanism, the request router says, oh, that's a transaction. I will forward it to a transaction coordinator. Again, there's a whole fleet of transaction coordinators for fault tolerance and for load management. Any transaction coordinator can take responsibility for any transaction, and that transaction coordinator is then responsible for pushing that transaction forward and executing it if it can. First thing the transaction coordinator does is it takes the transaction, writes it to a persistent ledger so that we have a record of that transaction being in progress. By the way, this persistent ledger is itself a DynamoDB table. Good. The transaction coordinator then invokes a 2-phase protocol. This protocol involves the participants of this protocol are all of the master storage nodes for any item that's accessed in the transaction. Okay, so for a write transaction, any item that's being put, deleted, updated, or checked its master storage node is looked up by the transaction coordinator, and it's a participant in the protocol. No other storage nodes are involved in the protocol in any way. In the first phase of the protocol, the storage node, the coordinator sends the item, the transaction out to all of the participants and said, can you perform this transaction? And what that means is they check their conditions. If there's any conditions that need to be checked as preconditions on this transaction for the items that they store, if those conditions check out, they return accepted. If those conditions don't check out, they return rejected. They also check what pending transactions they're aware of that may be trying to write the same item. If any of those conflict in a way that can't be resolved immediately, then they also will send out a rejection message back to the transaction coordinator. If the transaction coordinator gets accepts from all of the participants, then it moves to phase 2 of the protocol. In phase 2 of the protocol, it then performs asks each participant to perform the writes or the deletes or the puts for their part of the transaction. Let me see. Yep. Okay. There's something else I was going to say, but oh well. So what about fault tolerance? The transaction coordinator, nothing permanent gets written in the first phase of the protocol. It's only when we get to the second phase of the protocol that writes are done. And in the second phase, once the transaction coordinator has progressed to second phase of the protocol, then the transaction is guaranteed to be pushed to completion. Okay? And it's guaranteed to be pushed to completion because the transaction coordinator keeps retrying those writes on the storage nodes until it gets a positive acknowledgement. And the writes are idempotent, so when in doubt, if he gets a timeout, he hasn't heard from the storage node, he told it to do the write, maybe it did the write and the reply got lost, it's okay to ask him to do it again. Because we know that the storage nodes are going to do them exactly once if we keep asking them to do it. And so the transaction coordinator is immune to failures of the storage node. DynamoDB automatically already handles storage node failures. If one of the storage nodes fails, DynamoDB will bring up a new one, provision it. The transaction coordinator doesn't even notice that the storage node got changed out from under him, except for maybe some performance hiccup. So the bigger question is what happens if the transaction coordinator fails? As I said, we have a persistent copy of this transaction stored in the ledger. The transaction coordinator just has source state about the transaction. We have a recovery manager who periodically scans the ledger looking for transactions that have been started but are stalled. They haven't been completed in a while. If it finds one of those, it assigns it to a new transaction coordinator who takes over the protocol. This only happens if the protocol is already in phase 2. In phase 1, we can just abort the protocol because it's easy to do that. Okay, so this new transaction coordinator, as I said, can just push the protocol forward. It can behave as though none of the writes have been done because, as I said, they're idempotent. And it's even, because of that property, it's even okay to have multiple transaction coordinators trying to push the same protocol forward in phase 2. That's okay. So fault tolerance is pretty straightforward, but it doesn't provide isolation. Okay, just because we guarantee that these writes are going to be done in phase 2 doesn't mean we guarantee they're going to be done in the proper order. So what do we do about that? We use a technique, I adopted a technique that's been around for a while called timestamp ordering. And the basic idea here is that the transaction coordinators assign a timestamp to every transaction, and transactions execute, at least conceptually, in the order of their timestamps. This is a technique that was independently developed by David Reed and Phil Bernstein about 40 years ago, right here in Boston, by the way. They both were here. It's a very simple scheme. It's easy to reason about. Okay, transaction coordinators just read their current clocks, give that as the assigned time to the transaction, include that timestamp in every protocol message that they send to the storage nodes, and the storage nodes then take responsibility for ensuring that their part of the transactions execute in that order. Okay, of course, we have a fleet of transaction coordinators, as I said, so it's possible that two different transactions that have overlapping sets of items that they're trying to write may in fact go to different transaction coordinators Those transaction coordinators may have unsynchronized clocks, and that's okay. Beauty of the timestamp ordering is it doesn't depend on clock synchronization in any way. You get a serial execution order based on the timestamps regardless of clock synchronization. Having said that, however, you'll see there are some examples where if your clocks aren't at least reasonably closely synchronized, you may inadvertently abort transactions. So in fact, what we do, AWS has a time sync service. We use it to keep the clocks on our transaction coordinator synchronized fairly closely, say within a few milliseconds. And that's way better than we need in practice. So what I'm going to do now is I'm going to go through, show you some timelines, and show you some rules for accepting transactions or rejecting transactions that are used by the different storage nodes. In these timelines, what I'm going to show are, these are timestamp-based timelines. They're not the time at which messages in the protocol arrive at storage nodes. They're the time stamp that was assigned to different transactions that are trying to execute or that have been executed in the past, okay? And there's a separate timeline for each item in the system because each item in the system has a separate history of what transactions have processed that item and at what time those transactions were time-stamped. So in this particular example, I show 3 items, items A, B, and C, each with their timelines. Timestamps run from left to right. For item A, it has recorded the fact that transaction TX1 completed at some time ago in the past. For item B, TXB has completed more recently. And for item C, TXC1 completed at some time in the past. And there's also a transaction TXC2 that the storage node for item C has accepted, but hasn't yet completed. It passed phase 1 of the protocol for this item, but it hasn't yet completed phase 2 of the protocol for this particular item. And now what happens is when we get some new transaction that appears with its own timestamp, based on the timestamp of the items that are already known to each storage node and the timestamp of this new transaction that's trying to execute, each storage node independently decides whether or not it can accept or needs to reject this incoming transaction. It can accept it based on not only the conditions that it has to check, but also based on its history of transactions that it's seen in the past. And these acceptance decisions are made independently at each storage node. This is a property that I call independent serializability. And it's a very important property, as you will see, for the operation of the system. So let's look at some examples. Here's an example. We have some storage node for some item that has seen transaction TX1, that transaction completed at some point in time, and now some new transaction is coming in that wants to write the same item. There are 2 cases that we have to consider. This new transaction that comes in could have any timestamp, right? It's been assigned a timestamp by the transaction coordinator, but it could be a timestamp that's in the past. It could be a timestamp in the future, not just because their clocks could be off, but even with purely completely perfectly synchronized clocks, it's possible that the message got delayed in the network. It's possible that some failure of a node caused that node to hold on to the message, and when it recovered, it then resent the message. There's lots of systems issues that can cause messages to arrive in wacky orders, and the storage nodes have to be able to account for that. Okay, so as I said, there are 2 cases. Case number 1 is that this new transaction comes in and it has a timestamp that's old. That's older than the last transaction that this node has already performed. In that case, according to timestamp ordering, we just reject the transaction. You know, you're too old, get out of here. We'll see an example in a minute where we don't necessarily have to do that. And the other scenario is the timestamp, the new transaction has a later timestamp. We can accept it as long as that transaction's preconditions can be accepted at this particular item. If it has no preconditions on this item, we'll accept it immediately. If it has preconditions on the item, we'll check them. If those preconditions are met, we'll accept. If those preconditions are not met, we'll reject. This is the basic rule of timestamp ordering. If that's all we did in the system, we would be no better off than doing just conventional 2-phase locking. In fact, we'd be worse off in this example because with 2-phase locking, transaction TX1 has already completed. That means any locks that transaction TX1 had held in the past, it's already released. And so when this new transaction comes in, it can easily acquire new locks and immediately proceed. There are no cases with timestamp blocking in this scenario where we would reject the transaction, where with timestamp ordering, we would. And so why did we choose timestamp ordering? And the idea is we were able to adapt timestamp ordering to take advantage of the particular properties of the operations in a NoSQL store and get better concurrency and better performance. So let me give you one simple example here. Suppose that we knew more about this transaction TX1 than simply the fact that it completed. Suppose we knew that TX1, in fact, was a put operation that had completely overwritten the item. Now, if TX new had been performed before TX1, it doesn't really matter because anything that TX new would have done to the database, TX1 would have clobbered, right? So in fact, saying TX new executes before TX1 leaves the database in the exact same state as if TX1 executed without TX new executing at all. So in this case, since TX new is basically a no-op, as far as we're concerned, we might as well just accept it. It doesn't affect this particular item to accept it, but it may affect other items that are being updated by the same transaction. Okay? So the simplest thing is just go ahead and accept it, and then later, when the transaction coordinator comes back and says, oh, can you please do that right for TX new? We will say at this node, oh, we will notice that it has an old timestamp, and we will ignore it because it's obsolete. So this is an example of where you can get advantages from the semantics of put. If all of our transactions were just put and delete operations, then we would never reject transactions, even if they arrived completely out of order. What about concurrent transactions? Here's a scenario where we have a transaction that's completed at some point in the past. We have another transaction, TX2, that's been accepted. At this storage node, it's trying to update this item, but it hasn't done the update yet. And now some new transaction comes in that also wants to write the same item. These are conflicting transactions. Do we have to reject one of them? Not necessarily. Another beauty of timestamp ordering. Again, there are 3 cases to consider. The first one is the one we've already considered, that it has an old timestamp. We most likely reject it, except for the reasoning I just gave a second ago. If it has a timestamp, this new transaction has a timestamp that falls between the completed transaction and the accepted transaction. Can we accept it or not? Well, it depends. Whether this new transaction could possibly do anything if it were executed that might affect the accept decision for the already accepted transaction. It's not okay to ever unaccept a transaction once it's accepted, so we can't go back on that. But what we can reason is, can this new transaction, TX new, possibly take some action that might violate the acceptance of the already accepted transaction? And the only way it could do that is if the already accepted transaction had a condition on this item that it checked and was satisfied, and executing this new transaction ahead of it may have violated that condition. So if TX2 had a condition, then we'll reject TX new. If it didn't have a condition, we can go ahead and accept TX new and let TX new jump ahead of the already accepted transaction in the serialization order without causing a problem. This is an example now where we have 2 pending transactions writing to the same item that both have been accepted and both will be pushed forward. And then whoops, what did I do? And then the final scenario, of course, is the new transaction. This is probably the most common case, right? Because you expect timestamps to go forward. If the new transaction comes, it has a later timestamp than the already accepted one. Can we accept it? Again, it depends on whether it has a condition. If this new transaction has to check the condition of this item, but that item hasn't been written yet by the previous transaction, then we don't have enough information to be able to say that that condition is met, in which case we have to reject the transaction. If the new transaction comes in and has no condition on it for this item, then go ahead and accept it. Okay, so again, there are scenarios where we can have multiple conflicting transactions that would be tossed out. One of them would be tossed out in a locking scheme, but in a timestamp ordering scheme, we can allow them both to proceed. Allowing them both to proceed doesn't mean that we can allow them to execute, however, out of order. We still have to make sure that they at least conceptually execute in the order that they said they're going to execute in as defined by their timestamps. So let's look at a couple of examples of that. Here we have an example where you have two transactions. Transaction 1 wants to do a put on item A. It says A equals 1, B equals 1. Transaction 2 says put A equals 2, B equals 2. These transactions are running concurrently in parallel. They are timestamped such that transaction 1 comes first before transaction 2 in the execution order. They've both been accepted already by both A and B. Let's look at the timeline now of when these items are accepted and when they're executed at the individual storage nodes for A and B. Okay, so they both can be accepted, as I said, in parallel given the rule I just gave, independent of what order they arrived at the storage nodes. And now suppose at storage node A, transaction 1 appears and says, do this put for A equals 1. He does it. He does that do put for A equals 2. He does it. He got lucky. They happened to arrive at storage node A in the proper order. They got executed in that order. No problem. That's what we hope to happen. But now at item B, suppose transaction TX2 arrives first and says, please put B equals 2. What do we do in this case? Do we have to wait for transaction TX1 to arrive? No, we don't. Because it's a put operation. We can just go ahead and do it. And say, immediately, say, OK, we did put B equals 2. And then later, when transaction T1 arrives that says put B equals 1, we basically realize it has an older timestamp. We've already recorded the fact that the latest value of this particular item has timestamp assigned to TX2. TX1 is earlier. It's an obsolete request. We just ignore it. And we end up in the state that we wanted in our database with A equals 2, B equals 2, even though these operations arrived out of order at the storage node. We still were able to accept them and execute them immediately. Make sense? OK. But it's not always that easy. Let's look at another example. We got transaction TX1 is the same as it was before. Put A equals 1, put B equals 1. Transaction 2 now is update A to be A plus 1, update B to be B plus 1. The overall effect on the database is exactly the same, right? We end up with A equals 2, B equals 2, but the execution is different because now transaction 2 depends upon the execution of transaction 1 because it's an update statement. So if we look at the timeline again, we can accept both of them. If the updates arrive at the right order at node A, we're in good shape. But what happens now at node B if they arrive out of order? We get this update for transaction T2 that says increment B by 1, but we don't know what the value of B should be at that point in time. We do know that there's a pending transaction that we've accepted that has an earlier timestamp that's going to change this value, but we don't know what it's going to change it to yet. So what can we do? What we have to do is we have no choice but to delay the update until after the transaction 1 has executed, and then we can go ahead and do the increment value to end up with B equals 1 and then B equals 2. Okay, so here's an example of another type of way that we can manipulate the execution order to ensure that transactions execute in the right order, even though they were nominally conflicting. Okay, so that's for write transactions. What I want to do is say a little bit about read transactions. How do we process read transactions? We do it differently than write transactions. We could have used the exact same protocol. We decided to use a different protocol, as I'll explain in a moment. And that's why we have two different API calls for read-only transactions and write transactions. So we have the scenario where we have a timeline for an item. We have the latest transaction that has written that item as TX1. The timestamp for that transaction has been recorded along with the item. And now we get a read-only transaction in that's trying to read this value. Again, there are two scenarios. The read-only transaction could have been signed at a timestamp that's earlier than the previously completed transaction. It's trying to read a value in the past. This is where multi-version concurrency control would help us. We don't have multi-versions, so we have no option but to reject this transaction because that value is one that we no longer store in the database. The other option is we're trying to read a value in the future. That's OK. We'll go ahead, read the completed transaction, read its value, return it to the transaction coordinator and say, we're done. If all of the get operations in this read-only transaction fall into this second category, which hopefully they do, Then, and they expect to do in practice because timestamps are moving forward, then this read transaction, the transaction coordinator for this read transaction will accept responses from all of the participants in the transaction, receive the values read at that time from all the participants. It can take all those values, package them up, return them to the caller. We've executed, in the case of no conflicts or no contention, we've executed this read-only transaction in one round of messages, and yet we still provide consistent snapshot reads for it. But what happens now if it's a more complicated scenario where not only has there been a transaction completed, but there's been a transaction accepted, but not yet completed? Again, we have the three scenarios. We reject it if it's too early. We accept if it falls between the completed transaction and the pending transaction because that's the value we have. But there's another scenario where we have to reject this transaction, and it's because we're trying to read a value that's in the future. We don't yet have that value because it's based upon what TX2 is going to write, and so we can reject it. We do have another option, which you might consider, which is hang around for a little bit. Since this is a single-shot transaction, we knew that this write's going to happen pretty quickly, right? If it's been accepted, chances are the transaction coordinator is going to get back to us within a millisecond or so, a few milliseconds. So, you know, if we hang around for a few milliseconds, chances are transaction TX2 is going to come in, and then we can do the read. We decided not to do that. What we do is we reject the transaction. It goes back to the application. The application, most likely in that case, will retransmit it, resubmit it, because it's optimistic concurrency control. By the time that new transaction comes back in, TX2 will have already completed, and we're in good shape. So we get the same effect, essentially, but saving simplicity by making the system more simpler and putting the burden on the application to retransmit, which it's going to do anyway. So that's read-only transactions. I also want to talk a little bit about write transactions or about non-transactional operations. We clearly have applications that use regular DynamoDB operations that aren't part of a transaction. We have applications that are being written now that use a mix of transactions and non-transactional operations. And when they have that mix of operations, we want them to be serializable, just like transactions are serializable. How do we do that? Especially considering that non-transactional operations get, as I said earlier, routed by a request router directly to the storage nodes. They arrive at the storage node without any timestamp assigned to them, and yet we have to figure out how to serialize them with respect to other transactions. So let's look at how this works for writes. Here's a scenario. We got a transaction that's completed at this particular item. We get a singleton operation that's trying to write to do a put to that item. That put comes in without a timestamp. What do we do about it? It's easy. We can just overwrite the current value. We can accept that put immediately, do it. Conceptually, that put gets assigned a timestamp by the storage node that's just a little bit larger than the last completed transaction on the item. That's the easy case. What if there's an item that's been accepted already, but not yet written? This is the hard case. The put comes in. There are two possible scenarios where we can do it. One is we can conceptually try to perform the put before the already accepted item. But if the already accepted item has a condition that it's already checked, we can't do that because this put might have violated that condition, causing it to the acceptance to be wrong. In that case, we can try to do the put with a timestamp conceptually after the accepted transaction. But that doesn't work if the put has its own condition because we don't know how to check that condition yet. So only in this case, so in the scenario where both the put and the previously accepted transaction have conditions that have to be checked, one of them has to be aborted. We can't abort the previously accepted transaction, so we abort the put operation. So this is a new failure mode for DynamoDB where puts can be rejected due to a concurrent and conflicting transaction. I don't expect that to happen very much in practice. You know, I haven't seen applications that both do non-transactional puts and transactional puts to the same item in the same application, but it is possible, just to warn you. Now, what about non-transactional reads? The beauty of non-transactional reads is because the way our protocol works, we don't do any writes until phase 2 of the protocol. Therefore, we never have dirty data sitting in the database. And so when a read comes in, it can always read the latest value of the data. So no matter what, we get a get in, we conceptually assign it a timestamp between the last completed transaction and the next pending transaction, and that read gets done immediately, returns the current data in the database. That's the happy case. So far, I've been telling you about timestamp ordering and the benefits you get from a systems perspective compared to locking protocols. What I want to do a little bit is tell you about a couple of benefits that you get, not for the customers, the end users of the system, but for the developers of the system. As we were developing this, I realized that there were two key benefits to timestamp ordering. One, the obvious one, is that it's easy to reason about the correct serializability of the system. As long as you execute operations in timestamp order, you know that you're going to have a correct execution. I can't tell you how many times I had a developer come into my office and say questions like, do we have to introduce read locks and write locks and blah, blah, blah? And I would always ask them, okay, think about what you're trying to do. You're trying to execute these transactions in their timestamp order. Do you need locks to do that? Do you need separate them? And they would always go away thinking, oh yeah, okay, you're right. You know, it's because they're trained in school to think about locking, but after about a month or so of this, then I got them to think about timestamp ordering, and then the design discussions went much more smoothly. But the other property that I didn't come to realize the benefit of until much later is this independent serializability, the fact that you can take independent serial execution histories for different items and compose them together to get an overall serial execution history for the database as a whole. Clearly that has benefits from the implementation point of view, because it means you have to do less coordination across storage nodes. Our storage nodes never talk directly to each other in the process of doing a transaction. And it has implications for testing, because now you can test serializability as a local property on each node. So serializability becomes a unit test rather than a system test. That's a big benefit. But the benefit that I didn't realize until later in the game was that it has a big benefit for evolution of the system. We started, when we relaunched DynamoDB Transactions, with a simple scheme. We wanted to not introduce all the complexity that I talked about in this talk. We started out with simple acceptance rules with the idea that we would learn from our customers, figure out where are the contention points, and then add more complicated rules later on as we needed them. That means that we're going to be rolling out new versions of the service over time. We do rollouts live. We can't take the service down, ever. There are no maintenance windows in DynamoDB. We have to do live deployments while our customers are running, while we're still continuing to provide the SLAs. And this means that we do gradual deployments. We deploy new software out to a subset of the fleet, and then a larger subset, and so on until we hit the whole fleet. That means at any point in time, there's a potential point in time where we could have some storage nodes running one version of the software, different set of storage nodes running a different version of the software, and they're both participating in the same transaction. If we were rolling out changes to a locking scheme, that would be a nightmare. You'd have to figure out how the old locking scheme and the new locking scheme work together and whether they provided a correct execution for your transaction. But with independent serializability, it's no problem, right? It's okay if one set of storage nodes is using one sort of rules to accept and another set of storage nodes is using a different set of rules, as long as they both meet their property of the system, which is that they both guarantee local serializability for the items, the transactions that they're processing. That's all we need. And so this independent serialization property means that I can roll out new software without worrying about the correctness of it, as long as it's locally correct. That's a key benefit. Now what I'd like to do, again, is go back to the scalability concerns that we checked earlier and the concerns that people had. Recall that we had concerns about performance. Get inputs, as you see in DynamoDB, have no additional code. They go directly through the request router to the storage nodes, no impact on performance. Transaction get items have an extra hop through the transaction coordinator, but in general can be done in one protocol round. And so they have a little bit more performance hit than get and put operations, but not very much. Certainly not something that customers are concerned about. Transaction write items. The performance is independent of the size of the database, right? It only depended on the number of participants in the transaction. The number of participants is typically small. For the bank transfer example, it was 2. For the shopping example, there were 3 participants. No big deal. Transact write items have to do a couple of 2 rounds of protocols, and it has to do a couple of writes to the transaction ledger. And so in practice, you get a performance that's about a factor of 4 or so more than a non-transactional put. Factor of 4, our customers are delighted with that. It's like if you can do a transaction in a few dozen milliseconds, they're happy. So we have no problem there. So getting back to the question I raised at the beginning of the talk, can we have both transactions and scalability? Well, I've shown you how we've done it in DynamoDB. This notion of using timestamp ordering, single-shot transactions, allows us to add transactions to DynamoDB in a way that didn't impact scalability in any significant way. And so if we ask this question, I would say it's a resounding yes. And with that, I'm happy to stop and take some questions.
Please come up to the microphone to ask questions.
Hi, Danny Harnick from IBM. Is there an inherent limitation of mixing get and put operations in the same transaction?
Is there an inherent limitation in mixing get and puts in the same transaction? No. In fact, the transaction protocol, as I said, we could put gets and puts in the same transaction. Their advantage of having gets by themselves is that you can do a single round, but gets and puts in the same transaction doing the 2-round protocol would work just fine. We decided not to do that because we didn't want to complicate the API that we explained to customers, but there's no inherent system reason not to do it.
Thanks.
Hello here. So in a situation where you have a mixed transaction and non-transaction operations, say for example on the inventory table, maybe a warehouse has to clean up stock outside of customer interactions. How do you address the linearizability of both the transactions and non-transactional activities? As
I showed you, the non-transactional items are conceptually assigned a timestamp by the storage nodes as they arrive, and they execute in that same timestamp order relative to the transactions, and so it's easy to reason that they're serializable. Does that make sense?
Hey, Doug. Ime Wikbersman, Emory University. Great talk. Thank you so much. We know that some of the elusive aspects of making systems like that is defining the right interfaces. And I'm kind of curious about the transaction write. To what extent did you have trouble, or could you comment on the ability of developers to really understand their own preconditions? And did you guys think about making that simpler or inferring it from variables or something?
Yeah, so as I said, we did the API because it was it had the right properties that we wanted. We didn't want long-running transactions, but it does admittedly put a burden on the application developers to do this kind of mental transformation that I showed in the one slide, where you start with something that looks like a transaction and you turn it into a single-shot transaction. There are well-defined rules that we can give customers for doing that. What I'm thinking about now is, maybe what you're getting at is are there tools we can provide to allow them to write general purpose transactions, and then we automatically, under the covers, convert them into the regular single-shot transactions. That would be easy to do. I actually sat down to write that tool once and just haven't had the time to finish it.
Awesome. Cool.
Hi. Can you elaborate how you get the timestamps?
Can I elaborate how we get what?
Get timestamps.
Get timestamps. Yeah, so as I said, the question is how do we get timestamps? The timestamps are just taken from the current clocks of the transaction coordinator. So a transaction hits the transaction coordinator, he looks at his clock, he assigns a timestamp to that transaction. That timestamp is written with the transaction into the ledger and included with the transaction on every protocol message. It's as simple as that.
So it's a single point?
It's a single clock value. Yeah.
Single transaction coordinator?
No. There are the fleet of transaction coordinators.
So the clock must be synchronized to a very high
No. The clocks do not have to be synchronized even. Any unique ID you can use to provide a serialization order, right? If the clocks are not synchronized, then you get issues like I showed where transactions arrive out of order and they may be rejected more often. But for correctness, I could care less about clock synchronization. And the other thing that I mentioned is that we do, in fact, synchronize the clocks across transaction coordinators, so they're within a few milliseconds, and a few milliseconds is by far close enough synchronization to deal with transactions which take, orders of 30 or 40 milliseconds to execute. Yeah.
Could you say something about multi-region transactions? Do you see this extending to an implementation of that?
Oh, multi-region transactions?
Yeah, multi-region.
Yeah. So as I said, DynamoDB supports multi-region tables called global tables. Yep. I did that as well. And so naturally, I've been thinking about how transactions work with global tables. You can use transactions on a global table today, but you don't get global serializability. And so that's, a future work is what's the right model for that. I have some thoughts, but we haven't rolled them out yet.
Do you see the time sync requirement as being a limitation for extending timestamp ordering protocol that you just discussed?
No. As I said, time synchronization is not a requirement for correctness.
Thanks.
Yeah.
Why not choose enable add MVCC, giving multiple version? What's the choice there? Why
not do MVCC? Yeah. Multi-version concurrency control? The main reason is that Dynamo doesn't support multi-versions right now, so we'd have to change the storage node to support multi-versions. And also, there are concerns about the cost of multi-versions. It adds complexity. You have to decide when to get rid of the old versions, how long to keep them around, who's paying for that extra storage. Do we charge customers? Currently, we charge customers for storage. If we choose to provide, 10 copies of this version, 10 versions of this item, do we charge the customer 10 times for that storage, or do we eat the cost? There's all kinds of complexity there that we decided that we didn't want to bite off right now.
Hi, Pradeep from George Washington University.
Yeah.
So as far as I understand your talk, you are putting one layer on top of these storage nodes, which handles input and get. So if I take off-the-shelf key value store, let's say Memcache or Redis, how much effort do we need to support transaction on top of that? Can you highlight what changes would be in the key value store, what changes I need to have in the ledger? Because I think I need to bring a new ledger system on top of these key value store.
So I didn't quite understand your question. I think we're almost into the break, so why don't you come up and we can talk about that,
Sure.
okay?
More questions? No? Well, in that case, let us thank the speaker.